In this video, we will talk about the concept of overpotential, which is related to the chloride anomaly. As well, we'll also talk about batteries, but remember, in this case, a battery is a series of two or more cells linked together. First, let's discuss the background that leads to the chloride anomaly. If we look at the electrolysis of water, we find that water is both the strongest oxidizing agent and the strongest reducing agent. At the cathode, the water will be reduced into hydroxide, and at the anode, the water will be oxidized into hydrogen ions. If we were to do this in a beaker, we'll get two electrodes that would show bubbles. From the cathode, it would be of hydrogen gas, and of the anode will be oxygen gas. And the overall cell potential is 2.06 volts. This is going to be an electrolytic reaction, so the voltage is positive. However, if we do the electrolysis instead of in a beaker, we do it in something called a Hoffmann apparatus, then we can actually collect these gases. In a Hoffmann apparatus, which you may have seen before in grade 10, there is a glass apparatus that is similar to a shape of an H. We have two electrodes here on the bottom, and they give off gases. Remember that the cathode is going to generate hydrogen gas, and the anode is going to generate the oxygen gas. And you will see there should be twice as much hydrogen gas as there is of oxygen gas. As well, in a Hoffmann apparatus, the pH of the cathode will be greater than 8 due to the production of hydroxide ions. On the other hand, the pH of the anode will be less than 7, because the generation of hydronium ions or hydrogen ions. Again, in a Hoffmann apparatus for the electrolysis of water, there is a need for an external power source over battery because it's an electrolytic reaction. Now, instead of using a solution or a liquid of pure water, now let's see what happens if we do a electrolysis in a solution with sodium ions and chloride ions. This would set up for something what we call the chlorine anomaly. Let's look at the predictions first. We have sodium ions, chloride ions, and plenty of water. According to our reduction half table, water is going to be our strongest oxidizing agent as well as the strongest reducing agent, which is then very similar, exactly the same to the electrolysis of water. However, when we actually electrolyze a solution of sodium chloride using an inert electrode here of platinum wires, what we see is that in the cathode, we still get a collection of clear, colorless gas, and we react it positively to a Pap Test, which then tells us it is the presence of hydrogen gas. On the other hand, though, at the anode, a green gas is produced, and it smells of bleach. This would indicate that chlorine gas is being produced at the anode, which is different than our prediction of oxygen gas being produced at the anode. This is the definition of the chlorine or the chloride anomaly. Chlorine gas will be produced instead of oxygen gas in situations where chloride ions and water are the only reducing agents due to the overpotential. And this overpotential, also known as the half-cell overvoltage, is the actual reduction potential required for the reduction of the half-cell rather than the supposedly reduction potential for the water. Furthermore, we need a potential of greater than 1.5 volts for the oxidation of chloride ions instead of the 1.23 volts as predicted by the oxidation of water into oxygen gas. For the level of chemistry 30, we do not need to know the cause of this chloride anomaly. We just need to know that it will be present when we have chloride ions in a solution of water. Now, this chloride anomaly can actually be used in an industrial application. There's a chemical or company called Dow Chemicals outside of Fort Saskatchewan. They pump hot water deep into the ground into salt caverns, and they dissolve salt. And then they pump the brine or sodium chloride in solution form into reaction vessels where they apply electrical current. So then at the cathode, they would collect hydrogen gas as well to generate hydroxide ions. This would make sodium hydroxide. At the anode, they would collect the chlorine gas, and this is both the sodium hydroxide and the chlorine gas is useful in industrial applications. Here is the overall net balance equation. We have water reacting with chloride ions to produce hydrogen gas, hydroxide, and chlorine gas. The sodium ions that remains in the solution will be ionically attracted to the chloride ion to the hydroxide ions to generate sodium hydroxide. The chlorine gas that's collected can then be further reacted with the hydrogen gas that was also collected to generate hydrogen chloride gas. And when hydrogen chloride gas is dissolved into water, you'll recall that it generates hydrochloric acid. Hydrochloric acid is the laboratory name, whereas the muriatic acid is the industrial name, but is also HCl. As well, the chlorine gas can be used in a whole different variety of applications to make things like bleaches, plastics, pesticides, and industrial solvents. The sodium hydroxide, on the other hand, is called caustic soda. That is the industrial name. The chemical lab name is, of course, sodium hydroxide. And caustic soda is used in wood and paper manufacturing, dissolved lignin, which is a fiber in wood, as well as to use as a degreaser in various cleaning applications. Our last topic for this video is what happens when we add cells together. You remember earlier, when we add cells together, that creates what we call a battery. If these two cells are wired in series in a forward manner, that is anode to cathode, between the cells, then the voltages will be additive. Here, let's look at the cells of zinc and copper. Using our standard electrochemical techniques, we find that the voltage of the cell will be 1.10 volts. If we're to take 3 of these zinc copper cells and wire them together in series, so again, anode to cathode, and link them all into a voltmeter, we should see a total potential of 3.30 volt, because that's 3 times 1.10 volts. If instead we do not add these cells in series, we put them in backwards, in this case wire the cathode of one to the cathode of the other, and then the anode of one to the anode of another, then the strongest of the cell will be the voltaic cell, and the weaker of the cell will be electrolytic cell. So for example, we now look at the same zinc copper cell, but we'll now also look at the magnesium with the dichromate cell. Using our standard techniques, we assign the cell potential of the zinc copper cell to be 1.10 volts, and the magnesium dichromate cell to be 3.70 volts. If we're to link them from the cathode of one to the cathode of the other, and the anode of one to the anode of another, then the overall cell potential will be 2.60 volts, because that is 3.7 volts plus the negative 1.10 volt. Why negative? Because this zinc copper cell now becomes the electrolytic cell. And remember, for all electrolytic cells, we take the negative of the cell potential as we calculate it from the reduction half table. As an electrolytic cell, the mass of the copper electrode would actually increase over time due to the reduction of chloride ions into copper solid at the cathode. Similarly, the mass of the zinc electrode would decrease over time as it's slowly being oxidized to zinc ions.